which species would best act as a Lewis acid? So, we need to remember definition of Lewis acid. Okay, Lewis acid. So, what is an acid? Right, like HCl is an acid. Why? Because it donates a proton. So it goes to H plus, Cl minus. But in terms of the Lewis definition, this Cl accepts an electron pair. Right? It was bonded to an H. Now it has an extra lone pair of electrons here. That's definition of Lewis acid. So, also, that's what an electrophile does. So the term Lewis acid is synonymous or equivalent to an electrophile. It would love a lone pair of electrons to be added to itself. So we can examine these and figure out which one's an electrophile, basically. Which one has the ability to accept a pair of electrons. So B F4 minus, right? That's the same as B F F F F. That's boron with 4 fluorines. And boron usually has 3 electrons because it's in the, you'd like it to have 3 valence electrons around it because it's in the 3rd column of periodic table. It has 4 here, so that's why that's where the minus charge comes from. Right, but also it has a minus charge. It's not going to need much more electrons. If a nucleophile were to come along and try to get in here, it could not. Right, so we can look at, for electrophile, we can see, will a nucleophile be able to add as well? And that's another way you can think about it. So for B, hopefully we can see at this point that it is an electrophile because we know about carbonyl reactions, right? We know that this is an electrophilic center of this molecule, right? It has a partial positive charge. This O up here has the partial minus charge, right? And we can show that through resonance. We could also draw this minus CH3. Right? This is a ketone, and this is an enolate. After you move the charge around, move the electrons around, right? And all we did was go like this. That's just the resonance. But we can see the electrophilic center, right? So if we have a nucleophile with a lone pair of electrons, it can donate those electrons as a Lewis base would be donating electrons. That's a U there. And the acceptor of those electrons, this carbon, this molecule in the end, would be the electrophile. So B is an electrophile. It is a Lewis acid. It's going to be our answer. Let's keep going, though. Let's see. Let's look at CH3. So C, H, 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 radical. So I guess this guy, it could accept another radical, right? If you add, right, we know this can undergo like a radical reaction where we go, let's see, this guy would take one of these. I think one of them would go to H, right? And you could start a free radical reaction, but we want to accept a full electron pair in order to be a Lewis acid. So C should not work. That would be my explanation for it. CH3F, this right didn't work. So C, H, 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 F, right? F is like this, right? F meets the octet rule with 3 lone pairs and 1 bond, and C also meets the octet rule with 4 bonds. There's no room for a nucleophile to get in here, right? So it's not an electrophile, it's not a Lewis acid. So we can prove that too. And we're left with B as our answer.